The Enhanced Interior Gateway Routing Protocol, also known as EIGRP. In the late 1980s, IGRP was Cisco's routing protocol of choice. Now, IGRP was the predecessor to EIGRP. The problem was that networks were growing beyond the scalability of that protocol. The only choice was to migrate to a computationally intense link state protocol. Now, that caused some unique problems in and of itself. So, fortunately, Cisco did us all a favor and developed a balanced hybrid protocol known as EIGRP. In this nugget, we're going to start by defining exactly what EIGRP is. Then we'll take a look at a few of its unique components that qualify it as a balanced hybrid protocol, namely the tables associated with it and the diffusing update algorithm, also known as dual, that's used to compute the routes. After that, we'll take a tutorial on the configuration. We'll also take a short look at the different packet types associated with the IGRP, and then finally we'll look at the show commands used to verify operation in that protocol. As I had stated in the intro, the goal of Enhanced IGRP was to take the existing Interior Gateway Routing Protocol and allow it more scalability so that it can address larger networks. So what was done is they took the basis of IGRP, which was ease of configuration, neighbors, and the respect here was it only talked to its neighbors and it trusted what was known of the rest of the network through talking to its neighbors. In other words, other routers that are on the local area network or the wide area network directly connected to that router. Also, the advanced metric. Remember, we had the composite metric. We were going to keep a semblance of that. And the other thing was VLSM. This is variable length subnet mask. Simply stated, it allows the network to carry the mask on the update as well, so that as soon as you received an update, it didn't have to be class-based. And we're going to study class-based in another nugget in more depth. So we kept these essential characteristics of IGRP, but we had to improve two things, remember. And the first was we had to decrease the network overhead, and the second was we had to allow for faster convergence. All right, in decreasing the network overhead, this is what we did. We borrowed from the link state protocols and said, instead of periodic updates, which meant I set an update from my router out to every other router on the network, every n number of seconds, whether there's been a change or not, we went to incremental updates, and it says, don't send out an update unless a change has taken place. And when it does take place, only send it to the routers that that update or that topology change will affect, not everybody. So that was a big difference. Also, in those updates, instead of sending them broadcast-based, let's look at sending them via multicast. The difference there, broadcast will be sent and processed by everybody that is directly connected on that network, whether that's a LAN or a WAN. Now the difference there is local area network, usually Ethernet, and a WAN is serial connections. Now with multicast, it will reach everybody, but they will look at this address and they will say, you know what, that's not for me, and they won't process the packet, so it saves on overhead. The next issue we had to look at was faster convergence. Okay, multicast does help with faster convergence as well, but the big help is right here in dual. Now dual is the diffusing update algorithm. We're going to talk about it in more detail later in this nugget, but for now, just understand that it is what is used to find the best route or compute the best route in our networks. And with dual, it's going to have associated topology databases that are in addition to what IGRP would normally use. And then the rapid convergence is going to take place because of the way it processes the routes. And it has successors and feasible successors, which we will talk about in more detail later in this nugget. And then finally, reliability. Some of the packets associated with IGRP that are sent between routers will be reliable in nature. In other words, they won't be sent out on the wire and just hope that it gets there. There will be a required acknowledgement. If the acknowledgement does not come back from a specific router, then that will be sent again, this time rather than multicast, in a unicast packet. Remember that a unicast packet means that this router will address this router specifically. In other words, that packet is just meant for that one individual device. That reliability factor is key in the process of EIGRP, keeping convergence time at a minimum. Keep in mind, though, don't get confused. When we talk about reliable transport here, we're not talking about what you normally hear at the TCP versus UDP. At the transport layer, we're not talking about that connectionless versus connection-oriented. What we're saying here is it's RTP, the Reliable Transport Protocol, that is going to have an acknowledgement packet sent back to that router saying, I received this. It's not the three-way handshake usually associated with TCP. Just keep that in mind. All right. Once all of this was put together by Cisco, what the result was a balanced hybrid protocol. You'll also hear that termed an advanced distance vector protocol. Either way, they're talking about EIGRP and what was developed by Cisco. One of the biggest differences between enhanced IGRP and the original routing protocol is the number of tables it uses to find the best route to a given network. In IGRP, the original routing protocol, all we had was a route table. In fact, in all routing protocols up to this point, RIP, EIGRP, OSPF, we had a route table. All right. Now the difference here in EIGRP versus IGRP was the introduction of a network table and a topology table. Let me tell you exactly how these things are used. First of all, the network table. As soon as a router comes on a network, it's a brand new router, the first thing it does is it's going to send out a hello packet. Very cordial, saying, hello, I am this router. I am running EIGRP. Would you like to talk to me and run it with me? Essentially is what's going on, right? So any other router on that network that receives this packet is going to verify a couple of things before it'll call this other router its neighbor. Okay, so neighbor, there are some qualifying factors. The first is on EIGRP, they must be running the same autonomous system number. Now, an autonomous system number is assigned locally. Don't confuse this with the autonomous system number that you hear of for routing in an exterior gateway protocol, which simply means on the backbone of the internet, like BGP. That system number is registered with a body on the internet, and it has to be unique per company or per address space. This is a bit different. This is a local AS number because we're talking about a routing protocol that takes place in a company or in a network. So the network held behind here, in other words, a router that is the introduction to this network, and then all routers behind here and local area networks that have hosts on them, this is where the AS is going to exist locally. Now outside of here, on the backbone of the internet, that's where you have a global AS, autonomous system number, and that will be associated with BGP and the routing on that backbone. Okay, so it is different. The AS number has to match, and the other thing that has to match is the metrics that are used have to match as well. Simply stated, there are a number of metrics between K1 and K5 that are used by EIGRP to find the best route. To give you an example, what those are is K1 is bandwidth, K2 is the load, K3 is delay, K4 is reliability, and K5 is an MTU, which simply means maximum transmission unit. The good thing is, by default, the only thing that's used is K1 and K2. And those two, as I said, are bandwidth and delay. All right, so if both routers here are using that same metric, now we're going to qualify them as neighbors. Once that's done, it's going to be added to the neighbor table. So here's a new entry in the neighbor table. That's going to happen with every router on the local area network that hears this packet and has matches in these specific variables. So we're going to make this table up, all the neighbors that we know of. Now what's going to happen next is we're going to talk to those neighbors and say, hey, give me an update of everything you know about the network. So this router who is already in existence and has networks out in this direction, it could be a large network, is going to say, here, let me fill you in on what's happening, neighbor. And it gives it all the information, and it's going to use that information in its topology table. So a topology table is every route to every network in this large network. Okay, so it's very extensive. It's more than a route table because instead of saying, for this router to get to network A out here, I have one route, like you would see in a routing table. It's going to tell me about every route I have. Maybe there's a route here as well, so it's going to have one this way, and any others that exist as well. Okay? In that topology table, there are two states for each entry. One is passive and one is active. Really easy to understand here. Passive is when there's been no changes on the network and everybody knows everything about the network. It's going to jump into active state as soon as something changes and there has to be another computation to find another path. Now, if in our topology table we have two ways that we can go here, a plan A, which will run through here, and then also if that was to go down, a plan B, then we won't move into active state. We'll simply say plan A is down, we had a network problem here, we know of plan B, so let's run that way. And it'll stay in passive mode. So you can see already how we're going to allow for much faster convergence. No computation had to take place there to find an alternate path to that same network, even though we had a topology change or network down. Okay? Now, once we have this topology table fully populated, this is where we're going to use dual, the diffusing update algorithm that we talked about in the last whiteboard, to run all these metrics and figure out what the